inviting me here and taking me and my wife, Susan, around Kyoto yesterday and this morning. It was a very nice introduction to your country, which I think is fabulous from what I've seen of it. So I only wish that I had more time to spend, but maybe someday I can come back and spend some more time with you. It's a great pleasure and an honor for me to be here today. And what I'd like to do is to give you all kind of a mixture of a tutorial on tropical cyclones. I know many of you know quite a bit about tropical cyclones, some of you maybe a little bit less. And to try to bring you up to speed in some particular areas of tropical cyclone research that I happen to be involved with. And so I thought I would start today with something simple, but I want to reiterate something that Ito's son told you, which is, please stop me. Don't be the slightest bit afraid to say stop or raise your hand if you have a question, whenever, because the worst thing is for me to continue and not have you understanding me. And I admit to you that I'm going to be a bit tough on you the next 2 days. I'm going to demand a lot from you because I feel it's a very demanding subject. And I think that you will see that parts of my lectures are pretty mathematical because I believe you need to be to understand some aspects of these systems. And it can get a little bit rigorous. So stop me and slow me down. I don't intend to get through all the material I prepared. I probably have too much, but it's better not to cover it all and to have you understand what I do say. Okay? So the program is to give you a brief overview, just very, very brief so that we're on the same page, and then get into maybe some of the simpler aspects of the storms to understand, which is a very idealized picture of a mature tropical cyclone that in an idealized environment which is not changing, and we consider the storm to be steady and axisymmetric, and just think about the energetics and the physics of that, including the structure, what is the physics that determine the structure of the storm, and how the storms intensify. Now let me say that there are 2 lectures today and tomorrow morning, but they're not, I'm not separating the subjects that way. We'll just see how far I get today and then I will start again tomorrow. I provided everyone, I think they're provided with... so they're divided into 3 files, but they shouldn't be considered to be 3 lectures. It's just the way they happen to group themselves. So, but I will adhere pretty closely to that set of slides if you want to follow along that way. This is very basic, but it's important. What is it that we're actually talking about? Not everybody agrees on the definition of a tropical cyclone, but this is sort of my own way of looking at it. It's a nearly symmetric, that is circularly symmetric, warm core cyclone powered by wind-induced heat fluxes. We call that enthalpy fluxes from the ocean. And that distinguishes it from middle latitude or extratropical cyclones, which are powered by horizontal density gradients on pressure surfaces. But that may be a clean separation of definitions, but almost everybody who works in this field understands that there's a continuum. It's not just one or the other, but you can have storms that mix the 2 processes. Tropical cyclones that are undergoing extratropical transition can start to tap into the baroclinic energy source of middle latitude storms too. So it's not clean, but I'm going to stick to the extreme end of the spectrum in my talks and talk about the strictly tropical cyclone without the baroclinic, at least without strong baroclinic influences. Well, I think you're aware of the climatology of these storms. This is a set of tracks from the so-called historical or best track data set with colors that correspond to roughly to the intensity of the storm. These storms develop in the tropics, but they generally move westward and then turn poleward at some point. Not all of them do that. Some of them do. They always originate under very warm conditions in the tropics. but they can end up their lives as extratropical cyclones, or they die over land or cold water. I'm not going to be able to talk about it this set of lectures, but there are hurricane or tropical cyclone-like storms that develop with the same physics over high latitude oceans in winter. They're usually called polar lows, although that term is applied also to baroclinic storms, or Mediterranean cyclones, which are fascinating and develop under cold core lows aloft, but they're also powered mostly by heat fluxes. They're very interesting storms. I won't talk about them today or tomorrow because it's such a broad subject, this. If you look down from space, you can see nice photographs like this. That's been doctored by the scientists who work for NASA to give it a kind of a three-dimensional perspective. But when you look down from space, you see a swirling mass of clouds that maybe several hundred kilometers across. And you might see, if I can get the pointer to work here, it's that? Yes. You can see that, well, the deepest clouds, which extend almost from the sea surface to the tropopause, are in an annulus that we call the eye wall, around an often clear eye. And then the convection around the storm is often organized into these nice spiral bands. There's some evidence, by the way, that the ancient pre-Columbian Mayans and Caribs who inhabited the Caribbean region understood about spiral bands, even though they had no radar or satellites, obviously. So there's a bit of interesting history there. We've been flying aircraft into the centers of these storms since the 1940s. It's really beautiful when you look at the eyes of hurricanes. This is the eye wall, or the eye of Hurricane Katrina in August of 2005. This is the eye wall. There's often low clouds in the base of the eye. And then you're looking into the stratosphere up here. There's often kind of a waterfall or cascade of ice crystals that fall down the inside of the eye wall. It's quite a spectacular experience to see the inside of a typhoon. I sometimes think everybody should see this. So when I retire, I'm going to start a typhoon safari operation. So you can sign up after the course. Flying all these aircraft missions over the years has led us to develop these composite views of tropical cyclones. This is kind of a cutaway view with a satellite image at the top. You know, when you're at the top of a tropical cyclone, maybe 18 kilometers above the surface, oddly enough, it's some of the coldest air you can find climatologically on the planet is near the tropical tropopause. It can be minus 80 degrees centigrade, or 200 degrees Kelvin up there. So when you look down, you're seeing mostly ice crystals. But this cutaway shows the azimuthal component of the winds of a particular storm, measured by aircraft flying along these black dashed lines, and also dropping instrument packages called dropsondes. And so you can see the strongest winds are in a narrow annulus surrounding a pretty calm eye. And then the winds drop off somewhat more gradually, like 1 over the square root of the radius as you go out. And the strongest winds are very close to the surface, which is what makes them so destructive. The strongest winds are pretty close to the surface. This is not observations, this is from a model, but it shows the vertical motion. So you have strong updrafts, very strong gradients across the inner edge of the eye wall. I'm going to show you, maybe later today or tomorrow morning, that the eye wall of a tropical cyclone is in fact a good example of an atmospheric front. It is a region in which the dynamics of the system are actually trying to develop a discontinuity in wind. First order discontinuity in the wind. And it's only turbulence that prevents that from happening. In fact, in many ways, the strongest fronts that you can ever find in the planet, the eye wall hurricane. Although most of the discontinuity is not at the surface, but above the surface. Okay. Now this is an important diagram. This is showing a particular hurricane in the Atlantic called Hurricane Inez. And this is the center of the hurricane. This is distance from the center. It's in the unit of essentially nautical miles. That's unfortunately what people, even scientists, used to use those units back in the 60s when this diagram was made. This is pressure. And this is the equivalent potential temperature. Does everybody know what that is? Or should I say something about it? If you don't know, come and talk to me about it. If you take the natural logarithm of this quantity, it's proportional to the entropy of moist air. And that's a quantity that's conserved if there's no external heating of the air. That is, if there's no radiation or fluxes of heat from the ocean, and it's conserved under the phase change of water, unless that phase change is very irreversible. And one of the things that I want to try to get across to you is that hurricanes are not powered by the latent heat of condensation, despite what you might have learned before or been told. I feel very strongly about that. That's an internal heat conversion process. And it can power a cumulus cloud, but it doesn't power a hurricane. Not only that, we have been able to simulate hurricanes that have no water in them at all. All right? If you want to know more about that, come talk to me. It's actually fairly easy to do. These storms arise ideally in conditions of radiative convective equilibrium, because there's a discontinuity between the temperature of the air near the surface and I should say the entropy of the air near the surface and the entropy of air that's in equilibrium with the surface. And that can happen just as well in a dry system. So we have run simulations with basically the basic state is dry radiative convective equilibrium. So you have a dry adiabatic lap straight through the whole troposphere and a big temperature jump between the ocean and the atmosphere. You set the latent heat of vaporization to 0 to achieve this state. It's happy to spin up a nice tropical cyclone. No water, all right? So one of the first things you have to do is get off the idea that hurricanes are driven by latent heat. They are not, okay? Now, if you look at, we're going to talk about this in a minute in more detail, but if you look at the cycle, the energy cycle of this, air is generally flowing in, spiraling in the atmospheric boundary layer. And you'll notice, if you consider this state to be steady, just for the purposes of discussion, you'll notice that the entropy is increasing very rapidly in the eye wall here. And that's reflecting the thing that's really driving the hurricane, which is a flux of heat, mostly latent heat, from the ocean surface to the atmosphere. That air comes in, it then turns up and rises up the eye wall. And that process is very nearly moist adiabatic. It certainly is in models of hurricanes, and as far as we can tell from observations, that's also true. And then it turns and goes out, but it's also nearly following surfaces of constant entropy. So we'll come back and talk about this in more detail, but the important thing for you to know is all the entropy gain is in the boundary layer from air flowing into the eye of the hurricane. The very largest winds are here in the eye wall, and that's where the largest fluxes of heat from the ocean to the atmosphere occur. That's really what's driving the hurricane. That is why they immediately begin to die when they go on land. Okay? You cut off this heat source. Another important conserved variable that we will talk about, by the way, let me say as an aside, for almost any dynamical system you can think of, whether it's in the atmosphere or mechanics or some other physical system, usually they're easier to understand in terms of the most conserved variables you can formulate. So I'm not going to talk about temperature or water vapor because they're not conserved. I'm going to talk about entropy and angular momentum because they are not completely conserved, of course, but they're more nearly conserved. And this is showing you the distribution of angular momentum in a modeled hurricane. But we know from our tropical cyclone, we know from observations that it's similar. So the center of the storm is here. This is distance from the center, this is altitude in this case, and this is the quantity that is contoured. It's the absolute angular momentum per unit mass. Okay, so r is the distance from the center, v is the azimuthal component of the wind speed. So that's just the wind times the moment arm. This is the rotation rate of the Earth, or its projection onto the local vertical, and this is r squared. So this is the contribution from the Earth's own spin, if you will. And you can show that in a circularly symmetric flow, if you don't worry about the variation with latitude of this projection, it's really this is really just half the Coriolis parameter. This quantity is conserved following air as it moves along, unless there is a torque acting. So if we look at the airflow in this diagram, of course it's inward in the boundary layer, and then it turns up and goes out. But down here you'll notice that air is crossing angular momentum surfaces toward lower values. It's losing angular momentum. And that is because of the frictional torque between the rapidly rotating vortex and the surface beneath it. And that turns out to be far and away the most important energy sink in this whole system. It's the dissipation of kinetic energy in the atmospheric boundary layer. Well, then the air turns up, it flows along surfaces of constant angular momentum. Once you leave the boundary layer, there's not that much frictional torque. There is some. We'll talk about that later. And then it turns out, and as it flows out, it carries the low angular momentum of the core out. So you're way out here, you'll notice how anomalously low the angular momentum is. Locally, what you find is that V actually becomes negative in this region. That is, the air is actually circulating in an anti-cyclonic way. Now, I should mention to you that although I'm going to be talking about idealized hurricanes, in nature, rarely do you see perfectly symmetric anticyclones at the top of tropical cyclones, because there's always some wind shear, and that low potential vorticity air gets transported down shear, and it's very asymmetric. Jun Jae Woo, who's here, did part of his thesis on this kind of, it was very hard to get a symmetric anticyclone, right? You have a little bit of shear and it goes off, roaring off somewhere else. But we're going to stick to the idealized world for now, because we've got to walk before we can run. We have to understand the simple cases first, I think. Okay, by the way, even in this idealized world, this anticyclone never really becomes steady. It's always the outer boundary is always being pushed outward. And you start to get a lot of turbulence out here, which we'll talk about later, which acts to flux angular momentum from the environment back into the outflow. But it never really becomes steady. All right, so with that as a background, let me talk about the physics of the mature hurricane. And I'm going to start out talking about the energy cycle. And I'm going to refer to two papers, one very old and one that's only just now being released, okay? Some things change very slowly. But this is a paper that I wrote in 1986 in Journal of Atmospheric Sciences on the cycle, and then one that I've just worked on with a graduate student of mine, Raphael Russo-Risi, which you can find in the early online release section of Journal of Atmospheric Sciences. But it's pretty simple, actually, when it comes down to it. So let's go back to this picture that shows the vertical velocity cross-section, and I'm going to take this panel out, blow it up, and this is, again, a kind of an idealized cross-section. So the center of the tropical cyclone is here. This is distance from the center out to 200 kilometers. This is height up to 17 kilometers or so. And the colors are an ideal representation of this, what I call the moist entropy. I showed you a cross-section of before. The equivalent potential temperature looks like this. It's basically the one-to-one relationship between the two. And if you look at the circulation at the surface, it goes out a few hundred kilometers or so. We're going to start here at point A, which is in the boundary layer, with fairly low entropy air, and watch as we spiral in toward the center. And note that as you go from A to B, right under the eye wall, because you're in a cyclone, the pressure is dropping as you get close to the center. Now, if there were no heating from the ocean, you would expect the air to cool adiabatically, but it's not observed to cool adiabatically. It cools a little bit, but not very much. And that's because it's in contact with the ocean. And for the purposes of this discussion, we're going to consider the ocean temperature to be constant. Again, we're going to start simply. It rarely is constant. It turns out that a very important process in tropical cyclones is a feedback involving the ocean, where the hurricane drives very strong turbulence in the upper ocean, which upwells cold water to the surface. It's a fascinating and very important process, and it's a negative feedback on the storm intensity, because it cools the ocean. We won't talk about that here. We're going to stay in a simple, idealized framework for the time being. So this is a nearly isothermal expansion of air. But then it turns and it goes up the eye wall along lines of constant entropy, and that is obviously you're going from high pressure to low pressure as you go up. And that's a very nearly adiabatic expansion. Okay? So there's no heat being added or subtracted in this leg externally. Now, yes, there are large conversions of latent to sensible heat and to potential energy in this, but that's an internal conversion. It doesn't really enter into the energy cycle. The moist entropy is conserved. Theta E is conserved in this part of the cycle. Okay, and then now in nature, this is an open cycle. The very high entropy air gets exported and carried off to high latitudes often. But in a model, you can, if you go way out here, you can put a wall out here, and maybe not at 200 kilometers, you probably put it at 1,500 kilometers or so. And the air eventually will begin to come back toward the surface. And you can consider there to be two more legs. All this entropy that got put in down here gets taken out in the upper tropical troposphere by radiative cooling in a circularly symmetric system. So actually this happens mostly in the lower stratosphere, where the temperature itself is fairly constant. It's not exactly constant. But we'll consider this to be an isothermal compression leg. And then finally, it comes back down this leg B to A. Now, it's very interesting, and it's worthwhile to discuss this a bit. Technically, this is not anything like an adiabatic leg. Technically, what happens is the moist entropy declines a great deal because of radiative cooling, but then increases down here. I haven't shown this very well in the color scheme, due to mixing with shallow cumulus clouds. And so the tropical atmosphere outside the hurricane has a prominent entropy minimum in the low to mid-troposphere. And so there's a lot of irreversible processes that go along in this leg, all right? Nevertheless, the temperature itself, because this is true in the tropical atmosphere in general, is very close to being moist adiabatic on this leg. And so if you like to consider this to be an equivalent adiabatic leg, that is, if you only worry about how the temperature is changing along this leg, it's just as though that temperature change were brought about by a re-evaporation of water. Now, it turns out we don't really, in the end of the day, need to worry too much about what happens out here, but for now, we'll consider this to be an adiabatic compression. So if that's the case, then this is nothing but a giant ideal Carnot heat engine. And you know, Carnot heat engine is the most efficient engine for converting thermal to mechanical energy if it's operating between two fixed temperatures. In this case, the fixed temperatures are the temperature of the sea surface, around 300 Kelvin, and the temperature up here, which is closer to 200 Kelvin. So if you know your Carnot cycle, there's only so much thermal energy you can convert into mechanical energy. And that's called the thermodynamic efficiency. It's the inflow temperature minus the outflow temperature divided by the inflow temperature. So 300 minus 200 over 300, that's about a third. So in this cycle, about a third of the net heating from the ocean is converted into the mechanical energy of the winds. Now, there's something very interesting about this, which I won't labor over, and that is that in this idealized picture, this arguably isn't an engine at all. Depends on your definition of it. And the reason is it's not doing any useful work on anything. Instead, all the mechanical energy, or most of the mechanical energy you're generating, not all of it, just gets dissipated by turbulence in the atmospheric boundary layer. All right? So it's not available really to do any useful work on an external body. Now, it's not quite true. For example, the winds of a hurricane generate big waves on the ocean. And those waves will radiate out from the storm and carry energy with them. And that is, arguably, a loss of energy to the external environment. There are not very good estimates of this now, but I talked to my colleague Isaac Guinness at the University of Rhode Island. He thinks it may be as high as 15% of the energy that you generate goes into surface wave radiation. But in the spirit of keeping things simple, we'll assume here that it all goes into dissipation. And so it's not doing any useful work. It's like taking a steam engine that's supposed to drive, let's say, a water wheel to generate, to drive a generator to generate electricity, okay? And unplugging it from the generator is just going to spin really fast until the friction in the system stops the engine. Well, the engine might fly apart, but if the engine doesn't fly apart, it will just spin very fast and do nothing useful. In some ways, a hurricane is more like that kind of system. So, if you remember some thermodynamics, we have the perfect engine for converting thermal energy from the ocean into mechanical energy, isothermal expansion, adiabatic expansion, isothermal compression, adiabatic compression. And according to Carnot's theorem, the amount of power you can generate from that engine is the rate of heat input. This would be the flux of heat from the ocean, times this thermodynamic efficiency, the ocean temperature minus the outflow temperature, T0, divided by the surface temperature. So this ratio is about 1/3. Okay, and just to drum that in, if you look at the cycle in an entropy temperature space, here's A, your high temperature, and low entropy. You go from high temperature, low entropy to high temperature, high entropy. And this is the adiabatic ascent. This is the isothermal compression. And then this is the adiabatic compression. And geometrically, if you fix these two temperatures, the greatest area you have under this curve is if it's a rectangle. Okay? That's a way of looking at Carnot's theorem as a geometrical problem. So we could try to carry out this integral, if you will. So the heat input to the hurricane is this, Q dot. It's the integral over the surface area, that's 2 pi, times the integral of the heat flux, times radius, d radius. Okay, so this is an integral over the whole surface area of the hurricane, out to Carnot, of the heating. What's the heating? Well, it's the air density. This is the aerodynamic flux formula that tells you how fast heat is flowing from the ocean to the atmosphere. This is a dimensionless coefficient, which we'll call C sub k. It's the enthalpy transfer coefficient. This is a surface wind speed. And this is the enthalpy that air would have if it were saturated at the ocean temperature and pressure. And this is the actual entropy in the boundary layer. So this is one term. This is the driver. This is the heat flux from the sea. Okay? And it's proportional to the wind speed. But there's another term, and that's because most of the dissipation of kinetic energy back into heat. Remember, when you dissipate kinetic energy, you turn it back into heat. That's occurring in the boundary layer, and that can be shown to be proportional to the drag coefficient times the cube of the surface winds, if it's all mechanical turbulence. All right, so there's that term as well. In the steady state, this multiplied by efficiency has to equal the dissipation rate. The dissipation rate is just, again, the integral over the surface area of the storm times this dissipation of turbulence, okay? So now what we might want to do is let's go back to our diagram, or a slightly different form of the diagram. We could think about this as integrating over this whole cycle here. A, B, this is just a different picture, but it's the same cycle. A, B, C, D, okay? But we're going to do something a little bit different, because having an integral constraint on the energy is nice, but it doesn't tell you what you really want to know. You like to know things like the maximum wind speed in the hurricane. So we're going to do something a little bit different. This part of it's new, all right? This is the part I did with Raphael Russo-Rizzi. We're going to do two integrals. We're going to do the original integral I just described, and then we're going to do one around a slightly different circuit. We're going to start at the same point, but we're going to only go into a point B prime. Now let's consider B to be just a little bit inside the radius of maximum winds, and point B prime to be just a little bit outside of it, right? So we're going to go, the second time we do this, we're going to integrate from A to B prime. We'll integrate up from B prime to this point C prime, which is just a little bit below C, and then back down to the original points. Now it has to be remarked, if you remember some of the angular momentum and entropy diagrams, there's very strong radial gradients of entropy and angular momentum here. So the conditions at B prime will be perceptibly different from the conditions at B. And there are strong vertical gradients of angular momentum and entropy here. So C and C prime will be different. But out here, you're far enough out in the environment where the gradients are now very weak. So you can put a D prime and an A prime in there, but they wouldn't be very different from D and A. So we're going to do the Carnot integral twice, once around A, B, C, D, and the second time around A, B prime, C prime, D, and back to A. And we're going to subtract the second integral from the first. All right? Well, you can do that. When you subtract a line integral from another, what you get is a different circuit. It just goes B prime B, C, C prime, back to B prime. That's just taking the first cycle and subtracting the second cycle. When you do that, the conditions in this outer leg just go away completely. They become somewhat irrelevant. And all that's remaining is this little integral. Now you can make B prime and B arbitrarily close together. So take the limit that they become identical. And when you do that, you just get this formulation. So this now is only concerned with conditions in at the radius of maximum winds, or anywhere in this column that's saturated. So the dissipation rate is this. This is the Carnot theorem. It's Ts minus the outflow temperature over the surface temperature Ts. This is the heating rate. So we're saying that the dissipation of mechanical energy around this inner loop is equal to the Carnot efficiency times the generation. Well, you'll notice that the only wind speeds that occur there are the surface winds, the winds you multiply by the drag coefficient to get the stress, and by the heat flux coefficient in this guy to get the heat flux. It doesn't involve, there's no assumptions, that we've made no assumptions about balance, no gradient wind balance, not even hydrostatic balance. It's just energy, okay? Now you can collect terms here. This term has the same quantities as this term, but there's this coefficient. So you can solve this for v squared, basically, and you get this relationship, okay? Well, I've solved this for v cubed, but you can see that one of these v maxes cancels. And so you end up with this expression. Vmax squared is equal to this. So we call this Vmax the potential intensity. And its square is equal to the ratio of this enthalpy coefficient to the drag coefficient times the difference between the surface temperature and the outflow temperature, now divided by the outflow temperature. The reason that happens is because of this term here. So when you collect the two terms, then this becomes T naught. And this is no longer a Carnot efficiency, it's something different. And there's nothing wrong with that, okay? You're not violating Carnot's theorem because you're not doing any work on anything anyway, all right? There's no violation of that. And we call that the potential intensity, and it gives us some understanding of how to calculate the maximum wind speed if we know these coefficients, if we know the surface temperature and the outflow temperature, if we know the sea surface temperature, which largely determines this, and if we know the enthalpy in the boundary layer in the eye wall. Now, in point of fact, we don't know the outflow temperature, and we don't know the enthalpy in the boundary layer, so this is not really a closed expression. And we'll come back to that problem, okay? But you can at least evaluate this in a model, and we're going to do that next. So let me point out that these guys, the outflow temperature and the enthalpy in the boundary layer, are not quantities you can specify from the environment of the hurricane. They're internally determined, and I want to spend some time going over with you how they are internally determined, okay? But we can at least test that in models. And I want to go back and notice, sorry, I'm going the wrong direction now, that this is really valid between any two adjacent streamlines as long as they're in the air that's more or less saturated, in the region of the eye wall. The reason is that we've ignored irreversible mixing processes that occur along these legs, which become important once one of these or both of these legs are in the dry air outside the core of the hurricane. But they don't have to be exactly at the radius of maximum wind. So technically, this expression we derived should be valid anywhere sort of in the core of the hurricane, not in the eye, and not well outside the eye wall, but sort of in the core region of the ascent of the storm, not just at the radius of maximum winds.
So Kerry,
yes.
I have a question.
Yeah.
This morning we discussed what is the T out.
Yes.
Yeah. And what you're saying now is we can take the very local derivative. We can define the local derivative for this.
Yes.
And then in that sense, we can connect really outflow temperature can be if we can think it as T out. Does it make sense?
Well, the problem is that the reason I think it's unknown, let's go back to the diagram here. So there's several ways to look at this. You start at B, you go up. Of course, you're going up a moist adiabat, and you know the entropy. So if you know how high you're going, you know the temperature. But you don't know how high to go. You could speculate that you go to the tropopause, and it should be the tropopause temperature. We also know from observations that hurricanes locally modify the tropopause temperature. We learned that in Hurricane Patricia. We also, and I'm going to come back in a few minutes and show you this, when we run numerical models, we see that there's strong gradients of this when you go from one streamline to the next. The strong gradients of that temperature. So I want to leave it open for now, but come back to it. But there's no simple, in fact, I'm very tempted to digress about this. In 1986, when I was writing the paper I alluded to, I couldn't figure out what the outflow temperature was. And I puzzled over it for a long time. And then I had a conversation with a very famous man, Francis Bretherton. I don't know if you've heard of him. I know some people in this room have heard of Francis Bretherton. He was the head of NCAR for a while, for example. A very brilliant British scientist. And he happened to, and his student, Chris Brotherton, was my first graduate student, by the way, so it's a small field, right? Anyway, maybe Francis was coming to visit his son, who was then my student, I don't remember. But we had a conversation. I asked him this question, the same question that you asked. I asked Francis Brotherton. And he says, oh, that's easy. He says, you know, it's just these streamlines are asymptoting to the undisturbed value of potential temperature in the environment. It was easy, okay? And I said, yeah, that makes a lot of sense. And when I wrote the 1986 paper, I said, okay, that's what it's got to be. And it was only many, many years later that I understood that to be wrong. It's not what the models were telling us. And it's, in fact, much more interesting than that. But we'll come back to that.
Okay. I'm sorry, just the next one is a trivial question, but sometimes you use the entropy.
Yes.
And sometimes you use the
Enthalpy.
enthalpy. So
it's very sloppy of me. It's very bad. Can I use this board?
Sure.
So, just to be clear, moist enthalpy, leaving out some bells and whistles, is heat capacity at the constant pressure times temperature plus the latent heat of vaporization times the mass concentration of water, Q. So that's heat capacity times temperature plus latent heat of vaporization times specific humidity. It's closely related to moist static energy. If I added gravity times height, that'd be moist static energy. And the moist enthalpy, which I always use as the specific enthalpy, is more like, and I'm leaving off some small terms, Cp times log temperature minus the gas constant for dry air times the natural log of pressure plus LV Q divided by T. And I'm missing some small terms here. I can write the exact definition, but I spent too much time doing that. They behave somewhat similarly, and I fall into the trap of using them interchangeably, and I shouldn't. So you should stop me the next time I do that. For one thing, formally speaking, there is no such thing as a turbulent entropy flux from the sea. That would be considered by a thermodynamics expert to be a very sloppy way. There's an enthalpy flux. And if you take the enthalpy flux and divide it by the temperature, you get the tendency of moist entropy. So there's a lot of thermodynamic finagling here. And I'm afraid I'm being a little bit sloppy with the thermodynamics just to avoid having to spend a great deal of time on it. But one can do this very carefully and exactly. Okay. So I just wanted to show you these simulations, which are from my student, Raphael. And these are simulations with a cloud-permitting axisymmetric model. It's called CM1, if any of you use these models. George Bryan's model, it's a very nice model, and it's publicly available. You can get it from his website. If you're interested, you can write me or talk to me, and I'll direct you to the right place. And these are simulations showing time in days, and the peak wind in this sort of idealized tropical cyclone occurring in a completely uninteresting environment. And the difference between these four panels is the horizontal mixing length in a turbulence scheme. So that may seem like a very stupid, finicky parameter to look at the variability with. And I'll come back later and talk to you about why that's important. So this is 1,000-meter mixing length, so it's relatively viscous. And then we get to lower mixing lengths. And this black line is the actual wind produced by the model. And the red line is this quantity, the potential intensity that I show. But it's potential intensity that's calculated from the modeled quantities at the radius of maximum winds. It's not potential intensity that you know from the external conditions, because that would just be constant in time in this simulation. But what I want you to notice is that, especially when you get to these inviscid simulations, it's pretty close. Peak intensity is pretty close to this peak potential intensity. All right? So so far so good for that formula. It's not perfect, but it works pretty well for that. So the main point I want to get to you, across to you, is the energy source of a tropical cyclone. And it's not latent heat released in cumulus clouds. That's not it, okay? It's the flux of heat from the surface. These are flux-driven storms. They're driven by surface fluxes. When they go on land, the convection doesn't stop. It's the heat flux that stops, all right? And so you have to get out of the habit of thinking of circulations like this as being driven by latent heat release. In some ways, it's very attractive. You can formulate the energy cycle that way, but it's very difficult. And it's like any other physical system. If you don't use the most conserved quantity available, it's a much tougher problem. Let me give you a simple example. Is an ordinary elevator. So people know what an elevator is. It's a lift or...
I think
everybody knows what I'm talking about. So you know, the elevator goes up, a counterweight goes down. And if you take a freshman physics student and you say, how does the elevator work? That student might say, well, let's do an energy analysis. So let's look at the force on the elevator, okay? 95% of it is coming from the counterweight, and 5% is coming from an electric motor. So if we want to understand this to first order, obviously you throw the electric motor away, okay? All right? You can do that, then you're suddenly left with a system you can't predict at all, because you threw away the most important thing. And an advanced student would say, no, let's consider the counterweight in the elevator to be a single system, all right, driven by an electric motor. Now it's easy, okay? Now it's very easy. The whole thing works. And yet, when we talk about tropical circulations being driven by latent heat release, I argue we're making exactly the same mistake as the first-year freshman, where the counterweight is the latent heat release, or absorption, okay? And we insist upon that being an important source, and we are tempted to throw away. I mean, you can read papers from decades ago that say, well, 95% of the water vapor condensed in a hurricane is coming from outside the storm, and only 5% is locally evaporated. That's correct. And so therefore we throw away that 5%. You're throwing away the electric motor, okay, when you do that. It's much easier to make the moist entropy your working fluid and think about sources and sinks of that than it is to make the dry entropy the working fluid and have to deal with enormous but mostly canceling sources and sinks of that. You see what I'm saying? So always use the moist entropy or moist static energy as your working fluid variable, and the tropics becomes much easier when you do that. Right? Not just hurricanes, by the way, a lot of different systems in the tropics. I wanted to take the time quickly to do an alternative derivation of this thing to show you, to make an interesting point about this, is we're going to derive the same expression from a completely different point of view. And it's just from dynamics, basically. We're going to assume that the vortex above the boundary layer, but not in the boundary layer, is, at least not initially, is in gradient wind balance and hydrostatic balance. So again, we're going to define this quantity called the gradient angular momentum. It's the angular momentum the air would have if it had the gradient wind speed, which I'll call V sub g, and I'll define that in a minute. So this is the same, 1/2 F is what I call the MAGO for, sorry for the notational inconsistency there. And so if you write in pressure coordinates the gradient balance equation for a circular vortex, this is the gradient of g of potential height with radius. It's equal to the sum of these two terms, the centrifugal term, Vg squared over r, plus F, I'm sorry, that should be a V sub g there. I'm already finding a typo. That should be V sub g. And using the definition of absolute angular gradient angular momentum, you can show that this is equivalent to this guy. m squared over r cubed minus 1/4 f squared r. It's just an alternative way of writing the gradient balance equation. And we can write the hydrostatic equation this way. The vertical gradient of the geopotential is minus the specific volume alpha. Alpha is the specific volume. It's 1 over the density of the air. And the thermal wind equation is derived by cross-differentiating. So we take this expression and we take the derivative in pressure. We take this expression and take the derivative in radius and cancel the geopotential term. And when you do that, you get this relationship here. It's very easy to do that. I encourage you to do it yourself. M over r cubed times its vertical gradient is equal to minus the alpha dr. So just pay attention to this first part of the expression. Now we're going to make another third assumption. We've assumed gradient balance, we've assumed hydrostatic balance, and now we're going to assume something else. That is that the, let me write this, sorry to go back to the blackboard suddenly here, but let me write that you can take any state variable and express it as a function of any other two state variables. And I'm going to express it as a function of pressure and a new quantity called the saturation entropy. I'll call that S star. So that's this guy, the moist entropy of air that is saturated at the same pressure and temperature as the actual sample. Okay, so S star is just replacing Q by Q star, the saturation water, the amount of water vapor the air would have if it were saturated at the same temperature and pressure. It's a very handy variable. It's not conserved unless the air is saturated. And then, of course, it's the same as the entropy, and it is conserved. But it's a state variable. That is, Q star is only a function of temperature and pressure. So S star is also only a function of temperature and pressure. And you can express any state variable as in a homogeneous system as a function of any other two state variables. And so I'm going to choose to express this as a function of P and S star. Now, this gradient, d alpha dr, is by definition a gradient at constant pressure. I could have notated that. So d alpha dr at constant pressure is just d alpha ds star times ds star by dr, again, constant pressure. Okay, I didn't write that. I wrote that. I was pretty sloppy when I wrote that down. Hope you see what I'm saying. Now, here's the interesting thing. In the core of the hurricane, the S star surfaces are the same as the entropy surfaces. Entropy is conserved. Angular momentum is conserved. So both entropy and angular momentum are constant along streamlines. Therefore, they're just functions of each other. Okay. So S star can be written as a function of m, the angular momentum, alone in that case. And that's what I've done next. Well, actually, I did two steps in one, so I have to explain what I've done. I've written this as the alpha times the S star, and this is at constant pressure added, times the total derivative S star with gradient angular momentum, mg. I can do this because S star is only a function of mg in a steady state vortex. And then write dmg dr here at constant pressure. Now, it turns out that this assumption that S star only varies with mg turns out, unbelievably, not just to be valid in the core, but just about everywhere outside the eye. And the reason for that is that this is a condition for neutrality of the flow to the combination of gravitational and centrifugal convection. It's sometimes called the theory of slantwise convection. And that's a long story. And I don't have time to tell it here, but it means that in a general rotating vortex, if it's neutral to moist convection, then S star will only be a function of M everywhere where that neutrality applies. Okay, that's a theory of slantwise convection that was understood way back in the early 1950s. So it's much more general than just in the core of the storm. The final step is to make use of something called the Maxwell relation from thermodynamics. There are several of them. And one of them is that d alpha, the S star, at constant pressure is equal to the derivative of temperature with pressure holding S star constant. That essentially is the moist adiabatic lapse rate. It's the rate of change of temperature with pressure at constant moist entropy. And so that's how I got the equation at the bottom of this page. And that's valid if the flow is hydrostatic in gradient wind balance and is neutral to slantwise moist convection. Or you're in the core and you're along one of these ascending streamlines. Okay, fair enough. If you are with me so far, all we're going to do now is, let me just repeat that equation up here. It's the same equation, I've just written it at the top of the page. And I'm going to divide through both the left and the right sides of this by the derivative of m with respect to radius. And that's what you get. And this is just because dm dp divided by dm dr is just dr dp at constant m, or minus that quantity. And so I can write that equation alternatively as the second line, okay? And remarkably, I can now integrate that equation exactly along the angular momentum surface. So when integrated upward in pressure, starting from the top of the boundary layer, I can do that. The last term on the right is an exact derivative of pressure. ds star dm does not vary with along an m surface. If S star doesn't vary with m, then ds star dm doesn't vary along an m surface. So I can integrate this with pressure. And when I do that integral, I can write the result this way. So I'm integrating between the top of the boundary layer and sort of the top of the streamline. I'll denote that by the subscript O. So I'm integrating between two fixed points, and I get this expression. And the last step in this is to note that, is to go back and substitute for m its original definition, r times v plus 1/2 fr squared. And when you do that, you get this expression here, which relates the gradient wind at the top of the boundary layer divided by the radius there to the gradient wind in the outflow times the radius of the outflow, and then minus the difference in absolute temperatures times this all-important gradient of S star with respect to m. Okay? So the next step is to make a simple definition. We're going to, remember I integrated upward along the angular momentum surface to some arbitrary temperature. I'm now going to define that temperature as the place where the gradient wind vanishes. As you go out into the outflow, remember the gradient wind changes sign, it becomes an anticyclone. So we're going to look just where that gradient wind goes to zero, and that's what we're going to define to be the outflow temperature. We have a very definite definition of it, at least. We don't know how to calculate it, but it's the temperature that the air has when as it's rising, when its azimuthal velocity changes sign. It goes from a cyclone to an anticyclone. So if that's our definition, then we have the simple expression for the gradient wind at the top of the boundary layer, knowing that we still don't know the outflow temperature, okay? But we know how we've defined it in this case. And if the air in the boundary layer has the same entropy as the air just above the top, which is the condition for it to be neutral to convection, then we can alternatively write this in terms of the gradient of the actual entropy of the boundary layer with respect to angular momentum. So one of the things I want to say to you about this derivation is that in a tropical cyclone of these characteristics, the natural vertical coordinate is actually the absolute temperature. Remember, it's monotonic with height. It always decreases. That forms a natural vertical coordinate. And the natural radial coordinate is not radius, it's angular momentum. The whole mathematics becomes much simpler in that space. By the way, that can be generalized beyond tropical cyclones. In moist adiabatic atmospheres in general, the natural vertical coordinate is absolute temperature. If you write everything in that coordinate system, it's a lot easier.
Kerry, I
Yeah.
have just rather than
Sure.
issue, but I think this equation is very beautiful equation, and I love this one. But okay,
It's your
so
favorite
my
equation. Okay.
question is,
Yeah.
like here we can see ds over dm,
Yeah.
right? It seems to me related to the interplay of thermodynamics and dynamics.
Yes.
Right, but could you give me some more, physical image or understanding of this term, DSDM? Do you have any
I'll
good
try.
image
I'll try.
of this one?
Yeah, I'll try. In fact, that was going to be my next slide.
Okay, okay, that's fine.
Yeah, I'm going to try to do that. I would argue it's determined by boundary layer processes.
Okay, thanks.
And in general, as air flows in the boundary layer, as I showed you from observations, its entropy is increasing because of because of enthalpy fluxes from the ocean. And its angular momentum is decreasing because of frictional torque with the surface. And so the ratio of that sink to that source to that sink should give you the SDM. And that's essentially what we're going to do, is say that we can put the equation I just wrote in differential form. So we have this temperature difference times the rate of change, the total rate of change of entropy in the boundary layer, plus this m over r squared times the time rate of change of m, 0. That's just another way of writing that. So where does the SDM come from? Well, we can take conservation of entropy and write this as a vertical integral of that. So if we integrate conservation of entropy through the boundary layer, whose depth is little h, S star is just the vertically averaged entropy in the boundary layer, it's basically equal. There are two terms. There's the vertical integral of the turbulent flux, and if that turbulent flux vanishes at the top of the boundary layer, which by the way it doesn't in real hurricanes mostly, except in the eye wall, it can sometimes get close to vanishing, you're left with the surface turbulent enthalpy flux divided by temperature. And then you have our old friend, the dissipative heating. So those are the two big actual sources of entropy in the boundary layer. Similarly, for angular momentum, you integrate conservation of angular momentum to the depth of the boundary layer. We get, ignoring any turbulent flux of angular momentum through the top of the boundary layer, we just get the surface momentum sink times the radius. So that's the torque that the drag exerts on the system. So we're going to use this guy, and we're going to use this guy, and substitute them into this. That's all. And when we do that, we get our old friend that we derive from energy conservation, except that this is really here, if you follow through with it, it's some combination of the actual gradient wind and the surface wind speed. Okay? And the remarkable conclusion you get is if you're right that the hurricane is balanced above the boundary layer, it doesn't have to be balanced inside the boundary layer, then the gradient wind and the surface wind speed have to be the same. Now remember, this absolute value of the surface wind speed has a radial wind in it and an azimuthal wind in it. And the absolute value of the wind is the square root of the sum of the squares of the radial and the tangential wind. But the gradient wind is just a tangential wind. So what this is suggesting is that the magnitude of the surface winds in a steady vortex has to equal the magnitude of the gradient wind at the top of the boundary layer, or be very close to it. I don't know of anybody who's tested that observationally. It could be. There's enough data from aircraft and real hurricanes, you could probably have a go. You could test it in models, for sure. Okay? I don't think it's been done. I may be wrong about that. But this is just two different ways to think about it. Often, I think a really good understanding of a phenomenon happens from understanding it from two different angles, but which are physically consistent with one another. All right, so we derived a maximum wind speed from energy conservation, and we derived it from thermal wind balance and an assumption of slantwise neutrality. Really quite different derivations, but pretty much the same answer. Except we still have the problem that it's not close. We don't know what the outflow temperature is, and we don't know what the enthalpy in the boundary layer is. So I want to start at least, and then we'll take a break. I want to start in on the outflow temperature. This is actually a fairly recent development. I realized about not quite 10 years ago, I started looking at the output of full physics numerical simulations, that the outflow temperature wasn't what Francis Bretherton had suggested to me. There was something else going on, and that in any case it varied a lot from one streamline to the next. So what I want to start off showing you is what convinced me that we have a problem with that. Now the neat thing, I'm going to tell you one of my favorite science stories in meteorology from my own personal experience, is that when we figured out, I think, what's going on, it's very strange and non-intuitive in a funny way, and it solved a lot of problems all at once. When we figured out what's going on, a lot of dominoes fell. Oh, that's why this happens. This is why that happens. It cleaned up a lot of problems for us. When we figured out what was going on, it just solved a lot of problems. And it's kind of an interesting story. And I'll begin to tell it to you, and then we'll take a little bit of a break. I'm going to begin by showing you the observations. The reference to this is a paper I wrote with my friend and colleague Rich Rotuno, who's at NCAR, back in 2011. And so we're going to start with a numerical simulation with the same model I mentioned toward the beginning of this lecture. And this is a cloud permitting. It's not cloud resolving. It doesn't have enough grid points to do that. And besides which, it's axisymmetric in model, and clouds are not axisymmetric. Not usually. And this is just showing the spin up of the cyclone. So this is a model that has pretty high resolution and radius. I think it's 2 kilometers grid spacing, and maybe a few hundred meters in the vertical. If you want to run, this is not the CM1 model. It's a predecessor to the CM1 model. It's a model I wrote with Rich Rotuno back in 1987. Rich did really, it's Rich's model, not mine. And this shows the evolution of the maximum wind in a very idealized simulation of time. This is the maximum wind anywhere in the domain, and then this is the maximum surface wind. Okay. Now I want to mention a couple of things to you about this before I go on. In point of fact, when you look at these simulations, the peak wind anywhere in the domain can be quite a bit larger than the surface winds. Remember, the energy equation I developed for you gave you an expression for whatever wind speed you use to calculate the surface fluxes, a 10-meter wind speed nominally. Not the peak wind. Peak wind is somewhere higher than that, still in the boundary layer, but well away from the surface. These models show, as this one does, that peak wind can be considerably higher than the wind at the surface. So that energy bound, or the gradient wind bound, are fine for what they're supposed to do, tell you the maximum surface wind, the maximum gradient. They are not telling you the maximum wind anywhere. The maximum wind anywhere, for which there isn't really a good theory, in my opinion, happens a few hundred meters above the surface. Okay. And you can see the difference here. Okay, now what I'm going to show you is a bunch of cross sections of a hurricane in its mature state. So the first one shows this quantity I call S star, the saturation entropy. It's got a cap on the contours, so because otherwise all you see is the stratosphere where it's increasing rapidly. And you can see that there's a big hot core here, high values in the boundary layer, and these surfaces are kind of vertical in the eye wall. This is going all the way out to 1,000 kilometers, so the eye wall is way in the left-hand side. And these surfaces flare out. This yellow contour is a surface along which the azimuthal wind is 0. Okay, so it's a surface across which the azimuthal wind changes sign from cyclonic on the inside to anticyclonic on the outside. And you'll notice that where these S star surfaces cross V, okay? They don't all cross at the same altitude. They cross at a variety of altitudes. But remember, what we're interested in is not altitude, but temperature. So we're going to look at this in a slightly different way. Same simulation. This happens to show some streamlines here, but never mind that for now. This is showing the stream function, actually, here, black line. And this is the same line, except it's white now instead of yellow. It's the V equals 0 line. And then the important thing to notice is the shading in the background. This is the absolute temperature, which, even in a hot core hurricane, you can hardly see the hot core because you're still dominated by the fact that the temperature is decreasing with height. But here is what convinced me we had a problem. The uppermost streamline is in fact crossing this V equals 0 at pretty close to the ambient tropopause temperature. Okay? But as you go down, the temperature is palpably increasing, quite a bit actually, by 40 degrees Kelvin or so. So the streamline coming up just inside the radius of maximum winds is going to a very different outflow temperature. So clearly the outflow temperature is not a constant, but is a function of S star or M, as you please. It's a function of which of these, or stream function, which of these surfaces you're on. So the outflow is stratified. Its temperature is changing from one streamline to the next. Its entropy was clearly changing. All right. And what was stratifying the outflow? Brotherton said, we can sort of approximate this all as occurring at the same temperature. And it's clearly not true in the simulation. Okay. The outflow is thermally stratified in an important way. And it's not, even today, I think it's a little mysterious how it's stratified. All right. Yes, we know the entropy of the air coming up to one of your planes. Along each of these streamlines, we know the entropy. And so if we knew the altitude at which these streamlines were coming out, we'd know the temperature. But we don't know the altitude a priori. We don't know why why are they bunched up with this particular vertical gradient, which by the way is also related to the radial wind speed, and not bunched up all near the tropopause or some other arrangement. Why is it this particular arrangement? Another way to look at that is it's, this condition of S star being just a function of M can be rephrased as the potential vorticity, or the saturation potential vorticity, is 0 everywhere. And the whole problem can be phrased as inverting that potential vorticity subject to two boundary conditions, the gradient of entropy with respect to angular momentum, which we know how to do in the boundary layer, and the outflow temperature is a function of angular momentum, which we don't know how to do. So it's an important problem. We don't really know the upper boundary condition for this, and it turns out to be important. Not surprisingly, it turns out to be very important. One more glance, a couple of more glances at this. This is a peculiar diagram. The vertical coordinate is absolute temperature. The horizontal coordinate is azimuthal velocity. It takes a little while to put your mind in this coordinate system. And these are angular momentum surfaces. All right? This is the 0 line for azimuthal velocity. So what we're worried about is the stratification of temperature along the zero line. That's the definition of the outflow temperature. It clearly varies with angular momentum. And if we knew how it varied, we had completely specified the problem, basically closed the problem. We've given this whole vortex an upper boundary condition it desperately wants. Okay? It's an upper boundary condition in a coordinate system in which angular momentum is the radial coordinate, but still an upper boundary condition. So what determines the spacing of these surfaces? That was the problem that Rich and I confronted, all right? After the break, I'm going to tell you how we think we solved it, and then you can tell me if you think we did solve it. Okay. I think it's still a bit of an open issue. Just a few other observations here. This is a clue. This is showing a quantity called the Richardson number. It's a contour of that. It's a non-dimensional number. I've capped the contours at a value of 3 because you can get infinities in the Richardson number, for example. And I'm going to, in a minute, show you a scatter plot in this box here. I want you to notice this actually is where the upflow is occurring, and the hurricane is in this region here and starting to become an outflow. And in this region, the Richardson numbers are small. Now, the Richardson number is the ratio of the buoyancy stratification of the wind speed squared. If you've had some dynamics, you'll notice that when the Richardson number becomes smaller than some critical number, the flow becomes turbulent. And the effect of the turbulence in a system like this is to drive that Richardson number back toward a critical value. Okay, we see that in laboratory experiments. We see that in numerical models. Now, the turbulence is parameterized in this model. The parameterization is clever enough to know that turbulence should turn off when the Richardson number is above a critical value and accelerate if it's below a critical value. And in fact, if we plot, let me first show you, this is the same simulation, same model, where you're looking at the turbulent diffusivity produced by the turbulence parameterization. So it's very turbulent in the boundary layer, but there's a lot of turbulence aloft too. And the little box I just showed you is in a region of high turbulence in this model. Now I'm just going to show you the two quantities whose ratio is the Richardson number. The n squared, the buoyancy frequency squared, that's based on the dry potential temperature, and the wind shear squared. Okay, du by dz squared plus dv by dz squared. And this solid line is the Richardson number 1, and the points in that box all scatter along that line. Maybe not quite Richardson number equal 1, there's a bit of an offset, but they all line up, showing that the turbulence is indeed determining the stratification of the outflow. All right? That this is really bizarre, okay? In fact, I'm going to give this talk at the AOF, the Atmospheric and Ocean Fluid Dynamics meeting in June, to a group of people that don't typically talk very much about tropical cyclones, who don't know this. In fact, a lot of people who do talk about tropical cyclones don't know this. And I'm not even so sure, it's so bizarre, I couldn't be sure of it myself, but it seems to be true in the models. And by the way, we have some recent observations that suggest it's really true in real hurricanes too. But think about this for a second. I'll give you something to think about over the break. You have this macro vortex, and whose physics is determined essentially by turbulence. The all-important turbulent flux of heat from the ocean. And by the way, we've known that collectively as a community, I would say since 1950. There's a pair of papers actually by Herb Riehl and later by Ernst Kleinschmidt, a German physicist of that era, that showed pretty clearly that tropical cyclones are driven by turbulent heat fluxes from the sea. That's old news, okay? I think it's old news. Now we're saying something that a second role for turbulence is basically determining the upper boundary condition for the vortex, which you need if you want to truly understand its intensity and its structure. I've said nothing about the structure of the cyclone. But if you assume that the Richardson number is equal to some critical value, we'll say it's 1, doesn't turn out to matter much what you say it is. If you say that turbulence is keeping the flow near this Richardson number critical condition, you're saying that turbulence is determining the thermal stratification of the outflow. That, in turn, has a lot to do with both the intensity and the structure of the vortex. Think of how bizarre that is, okay? The turbulence way up in the outflow, which we usually don't pay much attention to in tropical meteorology, some of us do. We're saying that turbulence way up there has an awful lot to do with how the hurricane behaves, okay? If you don't believe me, I don't blame you. We'll come back and talk about that. How long should we break?
Yes, so
What about 5? Okay. Now it's 28, so what about until 35? We have 7
Okay, it's fine, whatever you say.
Okay.
If you don't like it, you can.
じゃあ40、あ、40。
Now try not to yell. Okay. It's got a loose connection. Yes? I will limit my wandering. Yeah, that's okay. How about putting it on my belt? That works? Yeah. Can't see what Oh, you don't have a
マイクの呼吸をポケットに入れるとマイクがちょっと弱くなる問題です。
How about that?
Okay. Great. Thank you.
All right. You can see how long that lasts.
Oh,
I didn't
before
realize
going
it was
into
off. Okay.
I got a question, or I should say, we got a question.
Okay.
I actually got many questions regarding Richardson number.
Yes.
How to interpret why you introduce Richardson number too? Because the problem was the constant temperature, outflow temperature was not good.
Yes.
The assumption was not good.
Yeah.
And then you check the particulate of numerical simulation and you introduced Richardson number.
I did.
And we couldn't
Figure out why.
Yeah,
Yeah.
so could you please explain
Sure.
that?
Yes, I did skip a step there. So when we looked at that outflow stratification, Rich and I came up with a hypothesis. And the hypothesis was that turbulence was setting the stratification. And we took our inspiration from laboratory experiments, where you start with a stratified fluid, like it's salty on the bottom and fresh on the top. And you put it between two plates, and the upper plate is moving relative to the lower, so you create a shear. And as you increase the shear, you get a large enough shear, and the flow suddenly becomes turbulent. And when that happens, you still have a mean stratification, but the turbulence seems to drive this particular number, this Richardson number, toward a critical value. And no matter how much shear you put into the system, the turbulence keeps the Richardson number constant. So that's result from laboratory simulations a long time ago, actually. And so we postulated that turbulence was setting the stratification, and the hypothesis could be translated to the Richardson number had to be near its critical value in this region. So that's why we looked at it. I failed to explain why we looked at the Richardson number, but that was the hypothesis. The Richardson number is constant. And now what I'm going to do is to show you what that implies. But go ahead, yes. Yeah.
But my understanding is that
Yeah.
the final goal
Yes.
is to estimate the outflow temperature.
Yes.
So how the introduction of Richardson number help to estimate the
Okay.
outflow temperature?
That's exactly what I want to try to cover right now. Exactly that point. Okay. So how do you go from why does the Richardson number tell you this outflow temperature? What we want is how does the outflow temperature vary with angular momentum, which remember is our radial, quote unquote, radial coordinate in this problem. So we can start by writing the Richardson number in these coordinates, in the angular momentum coordinates. So Richardson number can be written as, this is the stratification, this is essentially n squared. It's the dry adiabatic lapse rate times the vertical gradient of dry entropy. That in turn can be written as the moist adiabatic lapse rate times the vertical gradient of moist entropy. We've done two things here. Remember S star, this is basically the S star dz. S star is just a function of m. So we can write this as ds star dm dm dc. But dv dz squared is, at least to some approx, if you ignore the radial wind components, just dm dc squared over r squared. So one of the dm dz's drops out. Anyway, this is the Richardson number to some level of approximation, where the only thing we've done is to neglect the shear of the radial wind and looked at only the shear of the azimuthal wind. That's not necessarily a very good approximation, but we have to sort of make it to make some progress here. So we're basically hypothesizing that this guy is constant, which gives us a relationship between these two guys. Now we have to take this a few steps further. This is just turning the same expression around algebraically. We're saying that dm dz is equal to this guy times a critical, or divided by some critical Richardson number, which we're going to take to be 1. It doesn't really matter if you take it to be 1 or 1/4 or some number. It doesn't turn out to matter particularly which number you use, as long as it's in the right ballpark. But of course, m is just a function of s star, so you can write that as dm ds star. You can write ds star dz as ds star dm dm dz. You substitute from there, and you get this now. It's the same expression, just expressed a little bit differently. We're getting close, because what we want is dt naught dz. Well, remember, S star is just a function of temperature and pressure. So we need to go a few more steps here. Vertical gradient of saturation entropy is related to the vertical gradient of temperature, and it turns out, if you just write down the chain rule, write dt ds star is its gradient at constant pressure times moist adiabatic lapse rate divided by ds star dp. So that's just using the chain rule. And now we're going to use the definition of S star and the Clausius-Clapeyron equation to write this guy. Again, this is just from the definition of saturation entropy, and then the relationship between Q star and temperature from Clausius-Clapeyron. I skipped a lot of steps here, admittedly. But you can write ds star dz at constant pressure this way. I know this is a lot of math and a lot of steps here. But then you can write the whole thing this way. And then finally, or almost finally, if takes a long time to derive this, so I am deliberately skipping a lot of steps. You can go back to the paper if you really want to go. If the velocity is not too large, and this turns out to be a very large number here, we can neglect this guy and just focus on this term here. And so we're going to neglect the first contribution, and then we can write this as the gradient of the outflow temperature with respect to S star is just Richardson number times Vm ds squared. Okay, and finally, if we want, we can write this instead as a function of angular momentum. So we now have the outflow temperature dependence on S, and we use the simple fact that S star is just a function of M, and we can write it this way instead. So this is the boundary condition we're going to use. And it tells us how, remember that M is effectively our radial coordinate. So this is telling us how the outflow temperature depends on the effective radial coordinate. And it's a function that depends on the critical Richardson number, the radius at which we're applying this boundary condition, which is really the outflow radius, times dm ds star, which is determined in the boundary layer. We already know what this guy is. Okay? So this actually does close the system. It may not be the right hypothesis, but it does give us a boundary condition that turns out to be mathematically anyway well posed. It may not be the right physics. So we're going to see if we can come up with the whole solution. So we're going to start with this boundary condition. We're going to take the relationship I derived before the break, which is just the thermal wind relation. This is just expressing it slightly differently, changing it around algebraically, relating angular momentum, the boundary layer, to radius, and this gradient of ds star by dm. We'll take the conservation of entropy in the boundary layer, this guy, and the conservation of angular momentum in the boundary layer, this guy. So we have these, this, and that. And what we're going to do is combine, first of all, let me go back, combine these last two by basically taking their ratio into this expression. This is taking ds by dt and dividing by em by dt, essentially. So it's the ratio of the source of entropy to the sink of angular momentum. I might add something that you might have noticed, because when I did that, yeah, no, that's still correct, sorry. Now we're going to make some approximations. We'll let the boundary layer entropy be equal to the saturation entropy above the boundary layer. That's just assuming that the vortex is always approximately neutral to moist convection, which we already assumed in the gradient wind derivation of potential intensity. Now this is a little bit more radical. We're letting the surface wind equal approximately the gradient wind, although the equation suggests that that's right. And if we do that, we can transform this guy into this. And we have the balance condition, again, that we derive from gradient wind balance, or thermal wind balance. And if we eliminate V between this guy, the 15, and use this fellow at 14, we get this expression here. Okay? And finally, I mean, this is just a lot of algebra. We eliminate r squared between this guy and equation 11, which is back here. To put everything in terms of S star and angular momentum and outflow temperature, we get this. Basically, we get a quadratic equation for ds star dm. With this particular definition of just calling this chi, just a definition here. You can work this out. And of course, you can solve that quadratic equation. And we remember that we have a separate equation for the outflow temperature. And we can integrate that equation in from some outer radius, where this is the outer limits of the storm, where the velocity vanishes. And when we integrate inward, we're going to have to apply a boundary condition, and frankly, I don't know what the boundary condition this. So let me go back and tell you what I think I don't know. We're going to integrate this equation using dm ds star from this guy. Okay. It looks like we're going to have to do it numerically, although we're going to be able to get an approximate solution analytically. But to integrate this, you have to know a boundary condition. I don't know what the boundary condition is. So I'm going to make an assumption here, which I'm not very confident about, although the models show it's approximately true, that right at the angular momentum surface that comes from the radius of maximum winds crosses v equals 0 at the tropopause temperature. It's basically an arm-waving assumption. I don't have a lot of confidence in it. But I'll use that as a boundary condition, integrate that equation. And we can do it we can do it numerically, and I'll show you that we will do that numerically. If we make some additional approximations, that in the core, the velocity is much larger than the radius times the Coriolis parameter, that's a pretty good approximation in the core. We're going to ignore dissipated heating and ignore the fact that the saturation entropy of the sea surface is a function of pressure and not just temperature. If we make these approximations, it turns out, and I've skipped a lot of steps here, we can get an approximate solution. And I've written this in terms of angular momentum rather than velocity, but it's straightforward to convert that into velocity. It's basically telling you what the angular momentum is, at least its ratio to its value at the radius of maximum winds, epsilon, as a function of the ratio of the radius to the radius of maximum winds. And the only other parameter that appears here is the ratio of these coefficients. So in all potential intensity theory for the steady state dynamics, without exception, the only time you see the exchange coefficients is as a ratio. Now later, when we come back and talk about the time-dependent vortex, that's no longer true. The actual values matter, not just the ratio. For the steady state, all that matters is the ratio, and we know from many numerical simulations that that's approximately true in numerical models, going all the way back to Vikuyama's first successful numerical simulation of a tropical cyclone in 1969. At least I regard it as the first one that sort of got it right. A very simple, elegant, two-layer numerical simulation also showed that what matters is this ratio. And not only do you get that, but from the same set of equations, you get relationships between the outer radius, the radius where the winds vanish, and the maximum wind speed and the radius of maximum winds. And if the outer radius is much larger than the radius of maximum winds, this can be simplified. And then from that and the other equation, you can actually get a relationship between the maximum wind speed and outer radius and radius of maximum winds. And finally, at the end of the day, you get an expression for the maximum wind speed itself. So you're getting a structure and you're getting a revised expression for the maximum wind speed, which is the original expression here that we derived for, except that instead of this being a variable outflow temperature, this is the actual tropopause temperature, which we know in the environment. And instead of this being the entropy under the eye wall, it's the environmental entropy, which we know. So this is now an external potential intensity. But we've made some sacrifices to derive it. We've ignored the pressure dependence of this. And we've ignored dissipated heating, both of which are important. I'll show you that in a minute. So we weren't really right to ignore that. But you can run models where you turn off the pressure dependence of this and you turn off dissipated heating. By the way, even some really good numerical models of hurricanes today don't have dissipated heating. And I get very angry when I hear that, and I keep pounding on people. You've got to put it in, you've got to put it in. Oh, our storms become too intense. It's because you don't have ocean mixing. So we get into these arguments. But physics says you have to put it in. It's not some crazy idea, it's just ordinary physics. So this is modified by this funny function of CK over CD, right? It's a weird function. It looks like it's singular when CK is twice CD, because this goes to 0. And so this exponent goes to infinity. But on the other hand, when CK is twice CD, this is 1. So it's a limit in which this is going to 1 and this is going to infinity. What's that limit? That's a great ODE, singular limit problem. Turns out it's got a finite limit, and then this function is smooth across CK CD equals 2. It's just if you plot it, it's a nice smooth function. You don't see any singularity. Okay, so that's nice, and you also get an expression relating the radius of maximum winds to the outermost radius. By the way, I've made a goof here, a notational goof. We're calling that the same thing I called what I called the outflow layer radius. I should use a different symbol for that. This is the radius at which the vortex vanishes at the surface, way out there somewhere. And it doesn't tell you what the size of the vortex is. Okay, that's a free parameter. In fact, you can set either R0 or RM or RT, which is, remember, the radius where the angular momentum surface erupting from the radius of maximum winds crosses V equals 0. You can set any one of those, and the other two are determined. So it doesn't tell you how big the vortex is, but once, for example, if you specify the outer radius, it will tell you if the storm is at its potential intensity, what the radius of maximum winds has to be. So they all can be tested. But it's a property of almost every theory for tropical cyclones out there that it doesn't tell you whether it's a big storm or a small storm. It's silent about the overall size. It's not silent about the relationship between radius of maximum winds and outer radius. That can be theoretically determined, at least you can have a shot at it. It doesn't tell you whether, it doesn't tell you the whole dimensions of the storm. Nature is also pretty silent about that. I wish I had thought to bring pictures. You can take some of the tiniest tropical cyclones ever observed and put them entirely inside the eyes of a super typhoon. There's a huge range of sizes, big range of sizes of tropical cyclones in nature. It's huge. If you look at scatterometer data, which my former student Dan Chavez did, it's no good for looking at the inner core of hurricanes, but it's great for looking at the outer region where there's not much rain. So you can determine the outer limits of the circulation. It turns out to be beautifully log normally distributed in nature. We don't know why. Another of many mysteries of tropical cyclones. So I think about tropical cyclones the way Winston Churchill once defined Russia as a riddle inside a mystery wrapped in an enigma. That's what we have here. Silence, okay. Anyway, there's still a lot of mysteries in the tropical cyclone world. What do these functions look like? Oh, let me first say that the difference between the sort of the raw potential vorticity formulation and this is the raw one just predicts that the maximum wind speed should depend on the square root of this guy. But the revised formulation says it should be this much more complicated function, which has a shallower dependence. So one prediction of this theory is that the actual intensity of real typhoons, or numerically simulated typhoons with a good model, shouldn't be as sensitive to this ratio as it would be if it was just the square root of it. It's less sensitive than the square root. That's a testable prediction. And it has been tested, actually, and it is much shallower than the square root of CK over CD. This is what that, if you numerically solve the equations without those approximations, this is the sort of generic profile that's predicted. So this is the ratio of the azimuthal wind speed to its maximum value. And this is the ratio of the radius to the radius of maximum winds. So it has this particular shape. It goes to 0 at a finite number, okay? And then the dashed line, which you can't really see here, is the analytic approximation I'll show you an equation for. So the analytic approximation is not too bad. This numerical solution of the system has also been made ignoring dissipative heating and ignoring the pressure dependence of that. Now I want to show you that that's not a very good approximation to real tropical cyclones. So if you solve, go back and solve, let me just be very clear about what I'm doing here. Before I tried to get an analytic solution, we started off with a complete set of equations, basically. And you consider that to be, no, not those. Basically, these four equations. The upper boundary condition, basically the combination of these two is a lower boundary condition, and then this thermal wind balance relationship. It's a closed system. If you solve it for the steady state, you can solve it numerically exactly. And you don't have to make the approximation of no dissipated heating. When I say exactly, you know what I mean. Numerically exactly, it's not going to be numerical. It's always going to be a numerical approximation to the OD, to the differential equations. But you don't have to make the assumption that you don't have to drop this term, and you don't have to ignore the pressure dependence. So I wanted to show you what happens if you solve that numerically without making those approximations. Here. So this blue curve, this is now an actual wind and an actual radius, so you're familiar with that. The blue is when you have neither dissipative heating nor pressure dependence. The red is if you just add in the dissipative heating. So the wind velocity goes from about 60 meters per second to 70 meters per second. That's a lot. Remember, the destructive power of a windstorm goes up approximately as the cube of the wind speed. So that's actually a big change in destructive potential. And if you, in additional, you let the surface saturation entropy dependent on pressure, it goes way up. Okay. Now I want to talk to you just a little bit on the side about that. So remember when we derive the energy, part of the heating of air flowing into the center of the hurricane comes from the fact it's expanding isothermally. And so its potential temperature is increasing. And the saturation specific humidity depends not just on temperature through Clausius-Clapeyron, but on pressure. The smaller the surface pressure, the larger saturation specific humidity. So the saturation entropy of the sea surface goes up as the pressure goes down. Think about that. It's a positive feedback. So the more intense the vortex, the lower the pressure, but the higher, and as a consequence of the fact the pressure is low, the higher the saturation entropy of the sea surface, which is providing the flux. So the more flux you're going to get. If you get more flux, the storm's going to be more intense. Okay? And of course, it's balanced in nature because the dissipation goes up very quickly with wind speed, goes up as the cube. All right. Now, yes? Yes.
Okay. So, but I'm
Yes.
sorry, let me make sure, my understanding before going further.
Yeah.
So, you talked about the Richardson number.
Yes.
And it means, previously we have to think about the T out. But what are you saying sounds to me, for given Richardson number, we don't have to think about that kind of issue, right? Because the Richardson number gives you the stratification. So, but I think still, Richardson number should be observed or calculated.
Yes.
So I think do you think it's a given value or just how
Well,
can you derive the
so
Richardson number?
all we know is, the postulate is that in a turbulent flow, where the turbulence is shear-driven turbulence, in a stratified flow, the Richardson number tends toward a critical value. This is a laboratory observation. but it follows from the general idea of self-organized criticality. So I don't know how many of you are familiar with the beautiful theory. It's very intuitive. You know, the classical demonstration is if I have a big funnel, right, and I load it full of sand, and the sand comes out of the funnel and it starts to pile up on the table here, it forms a kind of a pyramid or a cone of sand, right? And you ask, what determines the slope of that cone of sand? Why is it not this, and why is it not that, but why is it this? It's because if you made it a little bit steeper, there'll be little mini landslides along that surface which reduce the slope. And if you make the slope too shallow, the sand will build it back up to a steeper. So it wants to be at a critical value, which is just the value that makes it just unstable to landslides. And you see this everywhere. Boiling water is self-organized criticality in a way. When you get up to 100 degrees C, so much of the energy is used to vaporize water, but there's none left over to heat. And so no matter how high you turn up your stove, you're not going to make the temperature much more than 100 degrees. It's just going to boil faster. Convection establishes a dry convection establishes a dry adiabatic lapse rate. That's another example of criticality. In a turbulent stratified shear flow, we observe yet another kind of criticality, which is the Richardson number criticality. So what we have done is to assume that's happening, armed with evidence that it's happening in models. And if you assume this, that gives you an upper boundary. You have to derive it, but it gives you an equation for the upper boundary condition you're looking for.
Yeah, I understand, but the
Yeah.
barrier
Yeah.
should be specified, right?
The what?
Barrier of Richardson number.
Yes, it should be specified, and you can change the number. And what we'll do is it will change that RT value, and that's all it changes. It doesn't actually change much else about the vortex. So what we did is we could have specified either the critical, it's actually critical Richardson number only appears in combination with R sub T. So we could have specified that, but instead we specified the outer radius. And everything else follows from that. So then the Richardson number just determines this internal funny number, the R sub T. It just doesn't turn out to matter what that critical value is very much. So it's kind of an interesting, I mean, I hardly believe it myself, except I don't know what else to believe. Nobody else has come up with a theory for this. There is no other alternative theory. Doesn't mean that there couldn't be. One of you might develop one. Right now there isn't. Or if there is, I don't know about it. Okay. And it solved a lot of problems for us. In fact, it solved one problem was the fact that the modeled dependence of the maximum wind speed on this ratio of exchange coefficients was a lot shallower than the square root, which we couldn't initially understand, but this theory predicts that. The shape of the wind profile in the inner region, I'm going to show you that it doesn't work in the outer region, but in the inner region, it sort of solved that problem. The relationship between the radius of maximum winds and the outer radius. A lot of problems sort of got solved. And I just want to and I wanted to say one more thing about this though, that in Earth-like conditions, this isothermal expansion gives you this heat input, which is a positive feedback. The stronger the storm, the more heat input, which makes the storm stronger. This is balanced in nature by negative feedback, which is the dissipation goes up very quickly with the wind speed as the cube of the wind speed. However, if you make the temperature of the system larger, the positive feedback from isothermal heating gets larger still. And at a particular temperature, it blows up. The positive feedback doesn't get balanced by boundary layer heating. And there is no solution to the equation for potential intensity. It doesn't have, it's a singularity. I call it meteorology's black hole. Okay, it's a singularity. And it happens only at very high temperatures, not temperatures we're ever going to experience. maybe water temperatures of 50 degrees centigrade, something like that. But we can simulate that, and we tried to, back in the early 90s, simulate with the non-hydrostatic model that I wrote with Richard, you know. And yes, if you make the water hot enough, something very dramatic does happen to the tropical cyclone. It becomes extremely narrow, more like a big tornado, 1 or 2 kilometers radius and maximum winds, and it goes all the way up through the stratosphere, up to the high stratosphere in height. And there's a lot of internal dissipation, which is absent from the theory, but it sort of takes over and saves you from a real catastrophe. And so it's a solution looking for a problem. It's science fiction in the best sense of the word. The equations say it can happen, but we won't observe one. I hope not. There's no conceivable. The only condition we fantasize you could get such a storm is if you had a big bolide impact with the ocean, the heated water in a local region to very high temperatures, which of course we have had in geological past. But that's another unexplored domain of tropical cyclone meteorology. But you have to be the sort of scientist who isn't content to study the Earth-like conditions and wants to look at the whole problem over the whole range of possible conditions. And I always encourage my own students not to be confined to the Earth, but to take any theory and press it way over Earth limits. And if all you care about is forecasting, there's perhaps not much point in doing that. But if you really want to understand it, there's a lot to be said for doing it. So we call these beasts hypercanes that occur in this supercritical regime. And we simulated them, but we got supersonic winds with a numerical code that wasn't designed to have supersonic winds. So if we want to do this properly, we have to have a better code that can handle Mach numbers greater than 1. Okay, finally, let me show you this graph, which was part of our attempt to test this idea. So what we're looking at here is the result of these simulations with a non-hydrostatic model, where we're looking at the wind speeds, and we vary this ratio in the model, Ck over Cd, the exchange of enthalpy to drag, from 0.5 up to 2. And as you can see, the larger the ratio, the stronger the winds. And this is exactly the same set of simulations, but we rescaled the peak wind speeds by this particular function of Ck over Cd, which, if this theory of Richardson number is correct, all these curves should collapse to the same curve. They don't quite, but they're much closer together here than they are there. Okay, so it does seem to obey the scaling laws you derive from this assumption of criticality. Anyway, there's a lot more work to be done on this problem. And as I said, I'm not 100% sure I believe it, even though it's kind of a beautiful idea, I think, that everything kind of works if you make this one radical assumption. Still, it's a radical assumption. I was just going to show you back to this pressure dependence. This is what it looks like if you try to solve that potential intensity equation, specifying a relative humidity in the boundary layer of 75%, and a particular ratio of Ck over Cd, and then solving for the potential intensity as a function of ocean temperature and outflow. This really should be tropopause temperature here. And this is the wind speed in meters per second. This is where we live, around minus 80, 30 degrees centigrade. It's somewhere in here, about 80 meters per second. If you lower the outflow temperature a lot and or increase the sea surface temperature, this is where this singularity happens. You can't solve the equation. We call that the hypercane regime. This is just a map in the real world of the annual maximum potential intensity. This is just looking at reanalysis data, monthly mean, including sea surface temperatures, and assuming Ck over Cd equals 1. Now, I want to say to you categorically, we don't know what it is in nature, and that's another whole branch of tropical cyclone meteorology I wish I had time to talk about, but I don't. When you get to high wind speeds, the ocean surface becomes an emulsion. You go from bubble-filled water to spray-filled air gradually. There is no more surface of the ocean, and nobody has a clue how to do heat transfer or momentum transfer through an emulsion. It's an unsolved problem. It's a very, very tough problem. So we don't know what CK and CD really are in the real world in a hurricane. We don't, okay? There are a lot of people who will tell you the same thing, not just me. So when you don't know, you assume the ratio is 1. What else can you do, right? But we don't know what it is. This is assuming it's 1. That's all. Anyway, so this is an energy theory. It doesn't tell you that there can't be tropical cyclones on the equator. It's as though the only thing I knew about an automobile was how fast the gas was flowing into the engine and the coefficient of friction of the car moving down the highway. Those are the two things I know, and I don't know anything about engines. I could put an upper bound on how fast the car can go, the rate at which you're supplying fuel to the engine, and the friction. It doesn't tell me that the engine works, okay? It's an energy argument. Potential intensity doesn't tell you that there can be a hurricane. It says if there is a hurricane, this is an upper bound on how fast it can go. But that upper bound has uncertainty because, for example, we don't know these flux coefficients. This is a snapshot. This is an August mean. And this is a January mean, so you can see something about the seasonal. I'm sorry, the color scheme isn't the same, so it's not quite fair to compare these two by color. This is a snapshot, not too many weeks ago, showing that if you look at an instantaneous picture of potential intensity, of course there's a lot of structure. What we don't know, and this would be simple for anybody to do, I think it is important, is how variable is it in time on short time scales. We know how it varies from month to month in the climatology, but what about from day to day or hour to hour? You know, it's not just the sea surface temperature. The atmospheric temperature is a very important part of the potential intensity calculation. Sea surface temperature you can assume is fairly slowly varying in time, but not the atmospheric temperature. The atmosphere is full of waves and things. So we don't know what the power spectrum of potential intensity is. That you could calculate, say, for radiosonde, island radiosonde station data. Another thing about potential intensity is if you look at it as part of the climate system in the long term, okay, you can express it in terms of climate variables rather than meteorological variables. So the way that works is the turbulent heat flux from the ocean on average conditions, not in a hurricane, is a balance between the net downward flux of radiation at the surface, the net upward flux of radiation at the surface, and entrainment into the ocean's mix layer, an entrainment flux of heat. Okay, now the potential intensity, if you substitute that into, remember the potential intensity is a function of this guy. If you substitute that in, you can write the potential intensity as in terms of climate variables, as this, basically now regard this as the difference between the surface and tropopause temperature divided by tropopause temperature, and the net radiative flux at the surface and the net entrainment flux divided by this guy. Okay. The greenhouse effect decreases the net upward flux of radiation at the surface. That's what it does. So that you already know that if you put greenhouse gas in the atmosphere, all of the things being equal, you're going to increase the potential intensity. And that's certainly observed. This is the mean surface wind speed. And there's this weak dependence on the surface temperature. But you can collect this if you associate the mean. Well, this is not the hurricane wind speed. This is the mean background wind speed, say the trade wind surface wind speed. So the way you increase potential intensity is you put greenhouse gases, you increase sunlight, that would do it. Or you decrease the mean surface winds. If you weaken the Hadley circulation, for example, that would decrease the surface wind. And so what you can do is you can just take this in a single column RCE model and calculate the potential intensity as a function of the wind speed or the greenhouse gas concentration or whatever. And if you like, you can plot the result as a function of sea surface temperature, which also varies with those things. But if you look at potential intensity varying with sea surface temperature by varying the surface wind on the one hand, and varying the radiation on the other hand, you get completely different slopes. And the message I want to convey to you here is you cannot interchange potential intensity with sea surface temperature. They are two different quantities. If you know the sea surface temperature, even if you know the outflow temperature, you don't know the potential intensity. There's a very sloppy tendency in the literature to mix these up. Sea surface temperature is the same thing as potential intensity. It is not. It is not. They tend to covary, but quantitatively, what's causing them, each of them individually to vary, makes a huge difference to the relationship between the two. So you can't say, okay, you know, it's 2 meters per second per, or 5 meters per second per degree SST. You can't say that unless you know what's causing both of them to vary. So potential intensity is not interchangeable with sea surface temperature, okay? Just not able to do that. And let me also show you, very briefly, that one question you can ask is, what does this have to do with real tropical cyclones? Okay? Well, the first thing you want to do is test it against real storms. So we're going to do that. There hasn't been enough of this, and what we're going to do is very simple. We're going to go and look at historical tropical cyclones in sort of the modern satellite era. And, you know, that's another long story. We're not doing a very good job measuring the intensity of real tropical cyclones, in my opinion, except maybe in the Atlantic where we have airplane recon. Okay, so we're going to forget about that for a minute and just take the historical, and we're going to look at the lifetime maximum intensity of each tropical cyclone in the historical record. And we're going to divide it by the potential intensity at that place in time from reanalysis data. So we come up with a normalized intensity. It's the peak intensity of the storm divided by the potential intensity at that place in time. And then we're just going to look at the probability or frequency distribution. So here it is. This happens to be for the Atlantic, but it has the same form in the Pacific and other places. So this is the normalized wind speeds, the lifetime peak wind speed divided by the potential intensity. And this is the number of instances where the actual value exceeded the value on this axis. So in this data set, there are 100 events whose lifetime maximum wind exceeded 0.3 times the potential intensity. And there are only 20 events or so whose lifetime maximum wind speed exceeded 0.8 times the potential intensity. And what you notice is these distributions fall along two straight lines. And if you look at other ocean bases or other subsets of the data, you always see that. In fact, if you take the original data, the hurricane data, and before you divide by potential intensity, you divide that originally into two sets, all storms that never made it to hurricane force, and all storms that did. So you have two sets. And then you do this analysis on both sets independently. This is what you get. These are the tropical storms, one beautiful straight line. It goes to 0 at a normalized wind speed of around 0.5. And the hurricanes are another straight line with a different slope that intercepted that 0.9. Now, what is this telling us? The fact that these are universal distributions says that the real world knows about potential intensity. That's lesson number one, I would say. Because these do tend to be universal distributions. You plot them for the Atlantic and the Pacific, they look the same. Number two, that the division between hurricanes and non-hurricanes may not be as arbitrary as I used to think that it was. There is something different. These distributions have different slopes. And you can see that in either of these charts. Okay. And that suggests that something does change in the physics when the storm gets to some particular intensity around marginal hurricane intensity. Okay? The fact that this intercepts 0.9 might suggest that the real value of CK over CD is 0.9 squared, or 0.8 roughly. Okay? That is, if I had assumed that the potential intensity of CK over CD was let's see, the square root of 0.9, I should have said, then this would intercept at 1, okay? And maybe this is trying to tell us that what CK over CD really is in hurricanes. And it may be telling us that what it is in tropical cyclones, and that it's a lot less when the wind speed is less. I don't know. We don't know why we see this. This is an unexplained result. It's robust. You can do it yourself. It's easy to do. I can give you tiny little scripts for calculating potential intensity from reanalysis data if you like. You can do it yourself. You'll get this, I'm sure, because I've had students do it. We don't have an explanation for that. You know? It's kind of shocking. Why this? Why that? Why the separation between tropical storms and hurricanes? Okay. Now I want to turn the subject to the structure of tropical cyclones. And this is going to be a bit of a short section. It won't last very long. I think you'll find it a little bit less rough going than what I just talked about. The outflow temperature theory is a pretty complex theory. If you didn't get what I talked about, I don't blame you, okay? It's not easy to follow. It's a lot of math in it. There's some interesting assumptions, but I encourage you to try to understand it, especially if you're interested in doing research, because almost nobody has followed up on this. Okay, and I think it's important anyway. But this one is not, I think, quite as difficult, although it's still very challenging. Why do we see the structure that we see? What's the physics that underlie the structure? Conceptually, I find it convenient to divide the storm radially into 3 regions. The eye, where on average the vertical velocity is negative. The inner core, which I'm defining as a place where the vertical velocity is positive. And then an outer region where, once again, it's negative. And so, you know, here's a satellite. That's not a satellite picture. I think it's an International Space Station picture. But there's the eye. This is sort of the inner core region. Almost all the rest of this is inner core. And if you go further out, where the deep convection goes away, pretty much I would say that's the outer region. In a loose sense, okay? These aren't very rigorous people. Other people have come up with similar divisions. Here's a picture of the situation. The eye has descent. There's typically a strong temperature inversion at low levels. Above it, the air is very dry. There are a lot of soundings taken in the eye. By the way, at least in the US, there's a rule that if you're running a radio sonde operation and a hurricane eye passes over you and you're still alive, you have to launch a radio sonde, even if it's not the regular time. We actually have quite a few eye soundings. Below the inversion, it's very moist, and you tend to have clouds at the inversion. This is the eye wall, which we've talked about a lot. There are rain bands out here, and then further out, there's a region of sort of large-scale descent and shallow convection. This is just a zooming in on the, this is a picture which is actually meant to explain or illustrate secondary eye wall formation. But there's something very interesting about the eye dynamics. I want to talk to you about that. Why is there an eye to a hurricane? Well, the real reason, which I'm going to talk about tomorrow, begins with the fact that, as I mentioned very early on, the eye wall is a front. And if you just let the axisymmetric dynamics take over without any turbulence, there would be a discontinuity where you'd have very strong winds in the eye wall and zero, literally zero everywhere else. And nature doesn't like discontinuities. It's horribly unstable. The three-dimensional eddies, or essentially barotropic instabilities, that flux velocity, angular velocity and angular momentum into the core. So the reason that we have the eye is in fact spinning is approximately the same reason a bucket of water inside a bucket is spinning if you spin the bucket. If you put a stationary bucket of water on a rotating plate, of course the bucket immediately spins, but the water inside it doesn't immediately spin because it has inertia, it just stays there. But of course you get strong shear at the edge of the bucket, you get turbulence, and that turbulence fluxes angular velocity into the body of water, and if you wait long enough, the water will be in solid body rotation. That's kind of what's happening, except for some very interesting deviations. So in a mature hurricane, you do have angular momentum fluxing into the eye, and it's balanced in the long run by the torque between the weak cyclonic flow in the eye and the sea surface. It's taking angular momentum back out. So let's look at an angular momentum budget for the eye. So let's just write an equation for partial derivative of angular momentum. We're going to integrate this through the boundary layer of depth h. If it's steady, this is 0. The terms on the right-hand side are the horizontal advection of angular momentum, the surface torque from drag, and this is an all-important term which is absent from classical boundary layer theory. It's the radial turbulent flux of angular velocity. So if you write down the Navier-Stokes equations in circular coordinates, this is what you get, where this, in the Navier-Stokes equations, this is a molecular viscosity, this nu, but we'll treat this as an eddy viscosity here, okay? There are ways of formulating that. I don't want to get into the details, but this is a very active term in mature hurricanes. It's not in classical boundary layer theory, which ignores horizontal turbulent fluxes in the boundary layer. This is very, very important. So you have these three things. You can use this to show that in the eye, the azimuthal velocity profile must be concave. That is, v has to go as, let's say, r to some power n, but n has to be greater than 1. Okay? So why does that have to be the case? So remember, we derived this equation just a few minutes ago for the wind profile in the inner core. Okay? And here is a picture of that. It does actually have an eye, but it doesn't have the right physics for the eye. So there's a profile there. We can sort of approximate in the inner core region this equation for the angular momentum balance. So we have the radial advection, and we're going to temporarily ignore the lateral diffusion. And we have the surface drag. And this tells us that the radial velocity, we just invert this, the radial velocity times the depth of the boundary layer has to be equal to the torque divided by the MdR. Once we have the radial velocity, we can use mass continuity to derive the vertical velocity. So if we apply this to the inner core solution, okay, we have this, first of all, we have this very interesting mismatch between the eye and the inner profile. And we get this solution for the vertical velocity. This is centimeters per second. This is all very reasonable. This is not. Out here, it produces much too much warming. And so we know this has to be wrong, because this is too much warming to be balanced by radiative cooling. The radiative cooling that would be necessary to balance that is much too large. Let me just go back a minute, because I've sort of lost the thread. The basic point I wanted to make here is that, let me go back back to this cartoon. In the steady state, we have a very interesting thing that these eddies are fluxing angular momentum into the eye. That's causing the eye to spin, and the cyclonic vorticity in contact with the surface produces an angular momentum flux of the surface. So you have this balance between the inward flux of angular momentum and that. To have an eddy flux of angular momentum inward, the angular velocity has to decrease inward. That means that the velocity profile in the eye has to be concave. If it's r to the n, then it has to be larger than 1. So the winds have to increase more rapidly than linearly. Otherwise, you can't balance the angular momentum better. So it's a very interesting set of balances. And in the steady state, thermodynamically, the subsidence in the eye is balanced by radiative cooling. This air is very dry because although you're mixing some water vapor in from the eye wall, not a whole lot. But now, because the eye is spinning cyclonically, you do have radial inward flow in the eye. And by mass continuity, you have to have upward flow. And so in the base of the eye, in the center of the storm, the air must be flowing upward. And it's observed to be. But higher up, it has to be sinking. And so what happens is you get a very sharp inversion. And I've always maintained that the altitude of that inversion actually has to tell you something about the intensification of the storm. If you have very rapid intensification of the storm, you're going to have a very large inward flux of angular momentum. You're going to be driving very strong descent, which actually warms the eye. It has to be warm as you intensify. You're going to get a low inversion. If the storm is decaying, the Ekman pumping wins. In fact, so much so that sometimes the eye fills with clouds, and this inversion has to either become very high or go away altogether. So what was thought you could use if you could invent a satellite technique for determining the height of the inversion, you might have a proxy, not for the intensity, but for rate of intensification or decay of the storm. That's just an idea. Okay, so that's some ideas. Now I want to switch, and I didn't really say this successfully, to what determines the profile outer. So the inner core, solution I showed you before the break, or just after the break, with the outflow temperature dependence of angular momentum, that only works in the inner core where air is ascending. It doesn't work in the outer region. And so something different is happening there. And there, by the way, moist hurricanes are very different from dry hurricanes, not in the core, but in the outer region. So what's going on out there? If the storm is steady, we actually have a constraint on the large-scale subsidence. That is, the subsidence warming has to balance the radiative cooling. So in the outer region, W is equal to what I call minus W cool. It's the radiative cooling rate divided by the potential temperature stratification. So this times W is the subsidence warming. That has to balance the radiative cooling. So how big W is in the outer region, which is defined as the region that's no deep convection, is the balance between subsidence and radiative cooling, just like in the Hadley cell subsidence region. That's a constraint on W. W can't be any old number. It basically has to be set by that. For the purposes of this discussion, I'm going to assume it's just a constant, okay? Of course, it isn't really constant, but we'll just assume it's a constant for now. It's not going to vary a lot, though. Okay, so you have that, but, and you can actually, so let me back up a minute. You have that, and on the other hand, you still have this vortex that extends to the outer region. Now, think about it for a moment. In the outer region, the vorticity is actually anticyclonic. The circulation is still cyclonic, but the vorticity is, relative vorticity is negative. That means there's Ekman suction. Right? The boundary layer physics is demanding subsidence. So we're going to come up with a really simple theory. For mass not to accumulate at the top of the boundary layer, the Ekman suction has to be the same, give you the same vertical velocity as the substance, the radiative substance. Okay? Now, that can only be true if the radial profile of azimuthal wind is a certain radial profile. And we're going to derive what that is. Okay? So we're going to begin by taking this radiative cooling velocity and deduce from mass continuity what that implies by the radial flow in the boundary layer. So the mass continuity equation in circular coordinates says that W is 1 over R times the radial derivative of R times the depth of the boundary layer times V. It's just mass continuity. We know what W is. It's this radiative cooling velocity. What does that imply about H times U? Implies whatever you get by integrating this. And so we can integrate that. If we assume that W is constant, we can integrate that directly. And we're going to integrate it inward from this outer radius, where we assume that U vanishes. And this is what you get. It's just doing an ordinary integration of this equation with W constant. So if the Ekman pumping balances the radiative cooling subsidence, it has to be associated with this radial velocity profile, all right? Now, the next thing is to look at what the Ekman suction really is. So Ekman suction can be derived by, again, assuming a steady state angular momentum balance. So the radial advection of angular momentum has to equal the surface drag. We're going to make the approximation the wind speed is the azimuthal wind. Not great, but we'll use it. And when you substitute UH from what we derived before, this equation can be written this way. So this says the radial gradient of this quantity, little m is just defined as RV, it's just for notational convenience, is twice the drag coefficient divided by this radiative substance velocity, m squared, divided by r naught squared minus r squared minus fr. So this is a nonlinear ODE. It's a Riccati equation, if there are any applied mathematicians. That's a notoriously difficult equation that was tackled by an Italian mathematician. It doesn't have an analytic solution, unfortunately. It just doesn't. But you can easily find it numerically. All right? It gives you a certain profile of wind. And Dan Shabas did his thesis on this pretty much. Comparing that profile to what you see in numerical simulations, it's absolutely beautiful how well it compares. And maybe it compares well because it's based on some very simple, robust physics. Radiation is limiting how fast air can sink. That has to match the Ekman suction. That demands a particular profile, radial profile of azimuthal velocity. That's all. And this is the profile. Integrating that equation gives you the profile. And so what does it look like? Well, here's one integration of this. This is the inner profile we derived earlier. This is the outer profile I just derived. And then the idea is that at the point where the vertical velocity changes sign in the inner core solution, so you transition from the inner core to the outer core, you transition from the inner core solution to this red outer core. So what really this is telling you is the effect of actual water vapor, or the difference between a dry and moist hurricane, is this tail. Okay? The tail is caused by the fact that in a moist atmosphere there is dry, stable stratification. Stratification along the moist adiabat stable. That limits how fast air can be sinking outside the hurricane. And that means you have to have a much broader wind profile to prevent heat and mass from accumulating at the top of the boundary layer. The hotter the system, the longer this tail. The dry stratification goes up much faster than the radiative cooling as you heat the system. So one prediction is that these tails will be much longer in hotter climates. And we see that in simulations, by the way. We have these much longer tails. It doesn't mean that the inner core isn't more compact or something else. It just means that relative to the core, you have a longer tail. And Dan was able to compare that kind of solution, this red curve, this thick red curve is the complete model matching of the inner core to the outer core, which occurs here, to various kinds of wind profiles in real hurricanes. If you're familiar with it, this is an H wind profile, and it's pretty good. Okay, so that is all I have to say really about the structure of the hurricane. So I think this is I know we're a little early, but it's a natural place to break. And tomorrow morning, if you're still up for it, we're going to talk about the spin-up dynamics. And finally, we'll end up with a discussion of how hurricane physics can be used to estimate hurricane risk.
Thank you very much, Kerry. So we're gonna get questions. Good time.
My goodness.
So
Yes.
I have a question about the equation 22.
Mhm. 22. I don't know how far back that is, but I'll find it.
For the structure.
Is it part of the structure?
No, before.
Before the structure, okay. That one.
So before the previous break, you
Yeah.
showed that the small Richardson number is responsible for the vertical diffusion in the upper
The
troposphere.
vertical stratification.
Yeah,
Yeah.
and responsible for the stratification and outflow temperature.
Yes.
But if the final product, equation 22, is independent of
Yes.
the Richardson number itself.
That's right. So that's a very good question to ask. Why is that so? All right. And let's go back to something that happened on the way to this derivation. Let's go backwards to, actually, I can't remember exactly where it is. So we had that, maybe it's, okay. So part of the solution to that is this equation here, which is a relationship between RT, or you can think of this as RT divided by Richardson number. It's probably the way I should have wrote. RT squared divided by this critical Richardson number is equal to Rm, okay? Rm squared times this ratio. We also independently have this relationship between Rn and R naught, in which RT doesn't exist. So we're left with a situation where I can specify R sub m and calculate R naught and RT, if I know the critical Richardson number. Or I can specify R naught and calculate Rm or RT, or I can specify RT. And what I chose to do in the solution is to specify this. And so I can get the Rm, and there's no R sub t in this relationship. And then RT can be calculated diagnostically afterwards, and that does depend on the critical Richardson number. But RT doesn't influence the maximum wind speed or the radius of maximum wind. So it influences the solution, but if I specify either R naught or Rm, right, if that's the way I go about doing it, the maximum wind speed doesn't depend on this. It's kind of remarkable, it's true. Where it does influence the physical structure of the outflow layer. That's where it appears. So it's doing that, but it's not really determining the maximum wind speed. Yeah. Tomorrow morning, I'm going to take the same model and make one change to it, is allow it to be time dependent. And I'm going to give you the model because it's really, really simple. I mean, remarkably, it says that 12 kilobytes is what it takes for storage. Do people have access to MATLAB here? On computers?
Yeah, not all, but
Not all.
yeah.
So those of you who can run MATLAB can I'll show you how you can download this model. And I think if you play with it enough, it's a very simple model, you can sort of see how this works. You can change the critical Richards number, and you'll see it doesn't really change the solution. This part of the solution, its influence is in the outflow layer. Okay? It really boils down, I'm not explaining this very well, maybe it's because at the end of the day, it boils down to the fact that in this whole mathematics, this critical Richards number only appears in combination with R sub t. So you can think of this as RT squared over the critical Richards number, and that's the only place it appears in the mathematics. And so changing, you can think of the Richardson number as changing R sub t and not changing anything else about the system.
So the RT is not dependent on the RI. So
It does. It does depend on the ROI. So in principle, the outflow structure should depend on the critical Richardson number. By the way, you could test that in a model. Because in some models, like the model I wrote with Rich Rotuno, in George Bryan's CM1 model, you can specify the critical Richardson number in the turbulence key. So the prediction is if you change that, you should change the structure of the outflow in a particular way which can be predictable. If you increase it, that means that the V equals 0 line should move outward, okay? Radially outward. If you decrease it, it should move radially inward without affecting the maximum wind speed.
Okay.
Yeah. So you can do it. If I had time, I could do it tonight, but so it's not hard. Yes.
So the vertical stratification in the upper troposphere is important to determine the temperature and outflow. But my question is, do you know if the numerical weather prediction models like HVAC, for example, is doing a good job in representing the vertical stratification in the model, or it can be one of the sources leading to the errors in the intensity?
That's an excellent question. Did everybody hear the question in the back of the room, just to be sure? Did you hear the question in the back of the room? Yes? Okay. It's very interesting you should ask that, because I've just been going back and forth with, I don't think the H-Wharf model, but the regular Wharf model. I don't know how different they are in this respect. The regular Wharf model doesn't actually have a critical Richardson number for turbulence. Instead, it has a diffusivity which is an extremely nonlinear function of the Richardson number, but a smooth function. So it doesn't turn off. You know, if you plot turbulence versus Richardson number, it's very high turbulence at low Richardson number, and then it falls very steeply, but not discontinuously. So is that going to make a big difference to the performance of the model? I don't actually know the answer to that question. It could, but we don't really know. But I will say the spirit of your question is just the right spirit, because we haven't paid any attention to things like turbulence in the outflow, a lot of attention in formulating models. We're trying to get the eye wall right, we're trying to get the surface fluxes right, all commendable, right? We've paid very little attention to getting the outflow right. And your point, we probably better get it right if we want to get the rest of the vortex right. I take that point.
The equation in this slide, the above equation, says that if everything else is same, if you go deeper into the tropics or close to the equator, radius of maximum wind is smaller.
Relative to the average.
Yeah.
Yeah. So I think the way to say what you said exactly correctly is either the radius of maximum winds has to become smaller, or the outer radius has to become larger. But I think there's an important caveat to that. This is a steady state theory. For the size of the storm to become equilibrated in numerical models, I haven't showed you this. Wind speed equilibrates over 10 days or something like that. But the size can take a long, like 100 days to equilibrate. And so my conclusion from that is that real tropical cyclones are never at their equilibrium size, except maybe by accident. So I don't think we can use this theory in the real world. Now, just to pick up on your question, there are these idealized simulations, I don't know, of aquaplanets. They're all ocean, the ocean always has the same temperature everywhere. And of course they have tropical cyclones everywhere, okay? It's like rotating RCE on a sphere. I can point you to those. Those tropical cyclones should have their equilibrium size. So you could test your idea by looking at those simulations. It's not the real world.
And because of this equation, the equation number 21, the last slide.
Yeah. See if I can find that
one
one.
back.
I'm going the wrong way, aren't I? Here we are.
So we have Coriolis parameter
Yes,
in the
denominator.
divisor,
Yeah.
but you can calculate maximum wind speed
Yes,
on the equator.
yes. That's right, and Rm goes to 0. So it's very unphysical. I mean, it has a mathematical solution, but it makes no sense. And again, the energy, this type of theory, in some sense, by predicting that Rm has to go to 0 as F goes to 0, shows it fails at the equation. By the way, I mean, let me just say, as an aside, there's a very I haven't really talked about it, there's a well-defined upper bound for how big a hurricane can be. And it's easy to understand. Try to make it bigger. The anticyclone becomes so powerful that all the energy goes into spinning up the anticyclone and not the cyclone. You don't get any surface cyclone. You don't see tropical cyclones that fill the whole North Pacific Ocean, for example. But nobody has a theory for the lower bound on a tropical cyclone size. We don't know how small they could be. So here's a challenge. Take a good axisymmetric model and try to make hurricanes smaller and smaller and smaller. You make the domain shrink, you make the spacing between grid points shrink. How small can you make it and still have a hurricane? And why? It's a wonderful problem. Nobody's tackled that problem. Some people think water spouts are hurricanes. Sorry.
So any other question? One more from you.
Back into Carnot cycle, Carnot energy cycle. The right-hand side, the substance, downward flow. Is it observable or is any observational evidence
For
of the
substance?
Yes, substance.
No, because we can't measure. I mean, certainly it's down in models. Let's put it that way. Numerical simulations, even three-dimensional simulations, there's a downward flow in the outer regions. But you can't measure vertical velocities because they're like there's like, trying to remember, magnitudes in the order of 10 millimeters per second. They're just too small to measure. But you can infer that they're downward.
But did you say the numerical model is?
The numerical model is downward in the outer region, yeah. It kind of has to be by mass continuity. You have a lot of air rising in the eye wall. If you've got a wall, maybe it's 2,000 kilometers away, still, air has to be sinking. Yeah.
And for example, tropical cyclone move at the edge of the Pacific High, for example, in the West Park.
Yeah.
Do you think that substance can enhance or maintain the Pacific High?
Oh, I see what you're saying. That's a good question. I don't know. I think the literature on extratropical transition sort of accidentally addresses your question a little bit. And then there's a big literature on how tropical cyclones penetrating the baroclinic mid-latitudes cause big ridging downstream or east of the tropical cyclone. And that's associated with the development of a surface high. I don't know if that's the same kind of anticyclone you're talking about, the quasi-permanent sort of Western Pacific anticyclone. I don't know if it plays a role in that, but yeah. there may not be enough tropical cyclones for it to be that substantial, I'm not sure.
All right. Think it looks okay. Okay, so let's give Kerry a big hand of applause.